So one neat trick to avoid doing work is to do videos instead, and that's what we're doing. I was talking to my buddy Adam on the Discord server earlier today, and we were talking about sort of the differences between understanding of things and how that plays out. And I brought up one of my favorite examples, which is latency versus bandwidth. Now, this sort of came up because I was just thinking about how much people don't know they don't know what's going on. They don't know how things work. They don't know what they're doing. They just don't understand the core technology. We're all building on the shoulders of giants. So the best example of this is to look up bufferbloat. Now, bufferbloat is an interesting sort of event to understand. And if you can find the original blogs by Getty S, read those because he, in order, goes through his troubleshooting techniques for this problem and how he figured it out. And this guy is basically the guy who wrote X Windows for Unix systems. And one of the things he says in one of his blog entries, and I still remember it all these years later, is he was surprised that people were still using X Windows because he wrote it in like the mid 80s or something. And he kind of figured, yeah, it would be supplanted by now. And then he was surprised to find out what people were doing with it. There were things he would have thought, as the originator of the code base and design, were impossible. So, interesting. And then people kind of don't understand the relationship between these sort of complex things, right? If you have, say, 1 gig of bandwidth on a line, say a cable line or something, but your latency is infinite, you can't use that bandwidth. In other words, you have 2 items and they both constrain each other in nonlinear ways. And this nonlinearity is very hard for us to understand in the modern science age of digital stuff. Because most digital stuff, at least on the surface, appears to scale very well. And I have a video on scaling. It's coming out on navigating patterns tomorrow. If you haven't seen navigating patterns, please take a look. I've got lots of talks with Adam there. Adam's a very smart young man, that's for sure. And our history talks are great. Also, my channel has exploded due to Mature Peugeot, a wonderful human being, giving probably what is the best YouTube watch this recommendation of all time. So I'm almost monetizable by one standard anyway. I've almost got 1,000 subs all of a sudden in the span of like a week, a little over. This is important because what Adam said really struck me. He said, oh, this relationship between the size of your pipe, your bandwidth, and the latency, the time it takes to get from point A to point B, reminded him of Fourier transforms. And I was like, yes, that's because a Fourier transform is a compression of two semi-independent variables whose constraints affect one another. And so when you compress that down, as you do it with fast Fourier transform, for example, there are some side effects and artifacts and things like that. Not that it's not super useful, obviously. Fourier transformed the world, literally. Like almost all the stuff you use is only due to Fourier transforms. To the availability of that fast Fourier transform, our algorithm, things like DAX and stuff don't work without it. So DAX are digital audio converters for those who I'm moving too quick for. So the importance of latency is just that, right? Understanding things like latency, and latency comes up in bufferbloat because it's an issue. That's the core issue. Actually, is actually best understood as a latency problem that affects your total bandwidth or total apparent or usable bandwidth. And it's called bufferbloat because it's a buffer problem. If bigger buffers lead to slower speeds, paradoxically, unless you understand the tech, in which case you go, duh, of course. Anyway, read that blog if you can find it. Getty S's blog on bufferbloat is just a fantastic lesson in proper troubleshooting of a technical problem. And one of the things I was mentioning in all this was, look, people don't understand. Like, you think, I'll just throw out a name, Eric Weinstein or Elon Musk is smart, okay? Van Jacobson, who wrote part of the TCP IP specification, was contacted by Getty because he knows him. They all know each other. They all built the internet together. These 10 really ultra smart people. Whatever you think of Eric Weinstein, drooling moron compared to these guys. No, really. Like, for real. Van Jacobson, when Getty told him the problem, like, fixed it the next day on code he hadn't touched in like 30 years. That's smart. Like, that's like smart. That's like, yeah. Whenever I, my ego gets up there, I go and remember that story. And I'm just like, I'm a drooling moron. Drooling moron. Nothing. I know nothing. Like, people that can do stuff like that. I saw Richard Stallman do stuff like that too. Like, oh, I know where that is. Blah, 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 edit this file. Blah, 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 line number, blah. It's right here. And I was just like, what? This is the source code for Emacs. You know where to change that line, what file it is, and what line number it is off the top of your head? Really? We were just out to dinner and chatting in the hall, and you come back here and do that? Holy shit. I don't know, man. You're around some of these people and you're like, yeah, I don't know anything. And it's the problem. Like, it's not that we don't understand latency and bandwidth and the relationship and how the constraints interact. And, it's like a full highway. You have a 10-lane highway. If it's full of cars, you ain't going nowhere. In fact, it's 10 lanes. Bandwidth doesn't help you. We don't understand this stuff. We just kind of understand, all this stuff is where we're going to start. We're going to take this for granted, like protocols, and we're going to build on top of it. And then you get weird side effects. Like, you get all these people, I think Discord does this. They build their protocols on UDP. It's like, why would you do that? If you know anything about the history of networking, UDP is for LAN. It's for local area traffic, LAN traffic. There's a reason for that, because it's broadcast-based, and if you lose for packets, you're okay. People will write UDP protocol because it's easy. Fair enough, but it's not session-based. So when you do anything useful with it, you have to add in error correction control and/or control and sessions, because it's not in that part of the TCP/IP protocol suite. Is it lower latency? Actually, it is. If it works, it's a big problem. In the early internet, in fact, nobody used UDP because, and by early internet, I mean like the early 90s, nobody used UDP because routers would deprioritize the traffic because it's supposed to be lossy. UDP packets are not supposed to be reliable. Reliable packets are TCP packets. There's a reliability section to the TCP/IP protocol suite, and there's a bunch of other stuff that's not supposed to necessarily be reliable. It's a bunch of protocols in TCP/IP. It's not one protocol. There's ICMP and IGMP and UDP and TCP, and there's a bunch of stuff. So most people don't know any of that. They weren't there. They didn't learn it, right? And so you have limits into what you can tune and what you understand and what you can debug. So there's the whole internet. All the big internet providers, cable providers, network providers, they're trying to fix the bufferbloat problem, and they can't. Getty did. Nobody else could. At least not of the people that knew about the problem were looking at it. And sure, that's not everybody. It's not every smart person or anything. But think about that. This incredibly fragile system is built on this code from a handful of people that nobody understands well today. My buddy recently had a problem. It was last year. It's a few months ago. And he was talking about the problem, and I was like, you might want to look at this little trick in the protocol that I happen to know about because I did some performance tuning for a company that I worked for. The bug affected Nginx. It was such an obscure protocol bug. I probably can't even remember all the details enough to explain them to you, even if I could explain them to you. And unless you have a real deep knowledge of TCP/IP, it probably wouldn't make any sense at all. But suffice it to say that there's a reset condition on a socket, that there's just a hole in the specification where you can get into, not technically a race condition, but it looks like a race condition. A race condition where config files can't be fixed and uploaded live. The bug got fixed mainly because my buddy pointed it out. He's one of the few people that could even understand such a thing, much less find it and propose a solution. He didn't get any credit, by the way. It's unfortunate. But these things happen a lot more than you are aware of. Nobody knew how it worked. Google couldn't fix it. Nginx couldn't fix it. They didn't understand it. The guys who wrote the Nginx code base, well, at least the guys who were managing the Nginx code base, did get fixed, but because of my buddy's work, right? And my fix didn't work, which actually I'm really curious about. I was tempted to go and reproduce it and see why my fix didn't work, because I was like, no, that actually should work. But there's, it's such a complicated technical thing. Like I said, I can't even remember all the details. It's such a freaking corner case. It was like a corner case of a corner case. It was insane. Yeah, I mean, there's so much complexity out there, and we just kind of take it for granted. Like, we don't know. We don't know what we're doing. All of this modern technology is built on so many key pieces of things that are supposed to just work. And we only know this little top layer. And like, there's an iceberg underneath of knowledge that you didn't even know was knowledge, right? It's the unknown unknowns, right? And that's there. That's real. That's a problem. Why doesn't this work? Why did spell check break? Spell check's terrible now. I mean, I know why. I told you earlier, actually, in an earlier video. When you use AI and LLMs, you're no longer spell checking words. You're actually creating more problems than you're solving, right? Because you're applying technology at the wrong layer. So it's enhancing bugs instead of fixing them. These are problems. Like, we're not paying attention to these things, and we should start. We really should. We really should get a better understanding of all this stuff, and we don't have a good understanding of it. It's very unfortunate. But it is what it is. Do you understand latency versus bandwidth and the limitations of each, and how limitations in bandwidth affect latency and limitations in latency affect bandwidth? I was telling the story about a problem we had on a T1 years ago, my buddy's ISP. That was copper, T1. They had fiber in New England back then, and he told them to keep a copper line. He deliberately said, don't pull out my copper. I want a copper backup in case the 2 fiber lines I have get cut. He had fiber from the north and fiber from the south from different providers. He was a complete psychopath. And then he had a backup T1, so he'd never be down. And he was never down like that. That ISP never went down in 0% downtime or something stupid. We came close once, but it never happened. Came within an hour of having both those fiber lines down. I don't know. He was very prophetic. There's another smart guy, my buddy Jeff. Really bright. So T1 wasn't sending, it was sending like 4K of data. It's a 1.5 megabit line, bidirectional, right? 3 megs total bandwidth, split in half. Turned out, very long story short, below the hardware protocol layer, which is the CSU DSU for the T1, in order to get those devices to work, CSU DSUs, they have to sync a clock. All technology relies on clock synchronization, not just GPSs. If you want to communicate digitally, you need a synced clock. Otherwise, you start to run into problems. They're not apparent right away, but they stack up pretty quick. If your clocks are too far off, things get weird and stop working. The the thing that calculated the clock syncing was using all of the bandwidth on the T1. How this is possible is, and how we found it was basically inference. Like, because you'd have to get an oscilloscope and measure the actual signals on the line. Because you can't measure it at the hardware layer because there's no software that can see the clock. It's taken for granted. The only way to see the clock is with an oscilloscope, for real. And then you'd have to know enough, like even if we had an oscilloscope, which we most certainly did not, we'd have to know enough about what a normal line looked like. That's gauge theory, the problem of measurement. Take one measurement, you know nothing. You need two measurements to kind of get. And the gauge theory is deep. You should engage with gauge theory. Haha. You need to know what a normal line looked like to know this one wasn't normal. And we didn't know that. Like, that's just blah. We know everything about the internet, like at a protocol level, no really, between the two of us. But we didn't know what T1 looked like on an oscilloscope. And you can always go deeper, like details, just go all the way down, boink, to the quantum layer, where then they become useless because they're not linear anymore. Hint about the world and what actually constitutes the world, by the way. Yeah, I mean, and that problem, it turned out to be a Cisco problem. Their top engineers wanted to talk to me. My buddy wouldn't let me. I was like, you son of a bitch. This is fun. This is a problem no one's ever going to know about or see again, or, whatever, right? This is like the deepest level of the internet type stuff. It turns out they did a software update and broke their previous syncing protocol, and they weren't aware of this. We didn't have Cisco equipment on the other side. We actually had a third-party vendor. My buddy was very cheap, and he was bright enough to get away with it, so it didn't matter. But we didn't have Cisco card. They only guaranteed the Cisco stuff would work with Cisco certified equipment, and we weren't using Cisco certified. We weren't paying 10 times what it was worth for the hardware. So we bought from a third-party vendor, who was a very good vendor. But they had broken the protocol in a way they didn't understand at Cisco, who updated all of the modern network protocols are basically Cisco controlled, just in case you didn't know that. So yeah, they wanted to talk to us, me in particular. Haha. Although Jeff did most of the heavy lifting with respect to helping to find the problem. And it just took two brains, because sometimes things take two brains. Most things take 3 or 4 brains. Just saying, the world is hard. It's really hard. Technology is really, really, really hard. I know a lot of technology. I couldn't have found that by myself. There's no freaking way. No way. So obscure. It's so like, how does this actually, like, what's the actual hydrogen mechanism of the sun? It's that level. It's that level of ridiculous detail that just, you reach a limit. But yeah, I mean, these relationships, and they're everywhere in life. They're not just in tech, right? These relationships where you have two things to make a third thing, but that third thing has 4 constraints, right? 2 in this dimension and 2 in this dimension. That's latency versus bandwidth, roughly speaking. That's the Fourier transform and what you're doing with the compression. And by the way, I told this to Adam. If you have a problem where Fourier is appropriate, you might want to look into wavelets instead. Much slower, but for a bunch of applications, wavelets are a better calculation than a fast Fourier transform if you need accuracy and precision. Just saying. Just research purposes. I've done the research, so I kind of know something about it. But that's what's interesting about these things, right? Like, you can only compress so much. In compression, there's a trade-off. And then you can only expand so much. Expansion, there's a trade-off, right? That goes back to scaling. And I think I mentioned this. Did I mention this? I got a video on scaling coming out on navigating patterns. So again, if you haven't signed up, jump on board this wonderful bandwagon to 1,000 subs. Tell your friends, tell your relatives. And watch my scaling video, because I'm going to go over some of it there. It will be less technical, but it gets back to scaling, because one of the things I was explaining too was, it turns out, and you can look this up, there's math behind it. I can't do the math. I hate math. Math is evil. But a big pipe, so say you have a gigabit pipe with 1 gig of, or gigabyte pipe or something, right? It's more efficient to lose a tiny amount of bandwidth and slice it up into like 10 pipes than it is to keep it one pipe. Because scaling doesn't work the way you think. And it just turns out that when you've got lots of different modes of communication going over a single line, while multiplexing is great, if you channelize the data, you can prioritize it. You can do special things with it. You can prevent collisions. There's all sorts of ways in which doing that small slicing and partitioning of the bandwidth, same way you do on a hard drive, by the way, at least modern hard drives, older hard drives didn't do this, by the way, actually makes it more efficient along some domains at the loss of efficiency of the top level domain for sure. But yeah, it's interesting. I'm not saying it's important. It can be important in certain domains. The amount of stuff you don't know, though, it's just dwarfs your knowledge by such an amount that it's not worth thinking about. Yeah. So little things to think about scaling, bandwidth, latency, how the world really works, troubleshooting. There's a bunch of little stuff in here. So I just thought I'd share that. That way I can avoid releasing my scaling video, which I have to write a description for, which means I have to listen to the damn video again. I hate listening to my videos. Oh my goodness. Most creators seem to hate listening to themselves. I'm no exception there. Because I didn't write a description when I listened to it the first time. I don't know why. I haven't figured that out. I was probably distracted. So I figured I'd distract myself with this, and hopefully you all find this helpful. And if you don't, then it's because there's too much latency.